welcome back. Welcome back to the world of RoboMate. So students, yes, we have been discussing the chapter circular motion. Now let us start with the next module of the chapter circular motion. In this module, yes students, in this module, we are going to derive an expression for the acceleration of a particle performing uniform circular motion by geometrical method. Alright, now students, in the last module, we derived the same expression using calculus method. Here we are going to use a different method, which is your geometrical method, and this is also there in your state book. Okay, now in this module students, we are just going to see the construction part of the geometrical method. In the next module, we'll go on to the main derivation. Is it clear? Can I start off with the module? Alright, fine. So we all know that UCM is an accelerated motion. Why it is accelerated? Yes, the direction of the linear velocity of the particle keeps on changing even though magnitude is constant. That is why UCM is an accelerated motion. We saw this. Now here for geometrical method, what I'm going to do is, I'm going to consider a particle. This particle is performing a uniform circular motion. In uniform circular motion, what is constant? Yes, very good. The magnitude of linear velocity is constant, but the direction of linear velocity keeps on changing. Is that clear? Now, let point O be the center of the circular path traced by this particle. Now, this particle is at position A. Now, OA will become my radius vector. Now, let us assume that this particle moves from position A to position B in a very small interval of time, delta t. In a very small interval of time, it moves from position A to position B. Now, OB will become my radius vector. Now students, as you can see there, the radius vector has swept through an angle. Yes, what angle? Very good, the radius vector has swept through a very small angle, delta theta. Small time, small angle, delta theta. Now students, the length of the arc traced by this particle, the length of the arc traced by the particle is delta s. That is also very small because time is very small. Now, the length of the arc can be denoted as a straight line. Why? Because students, time is very small, and in a very small time, the length of the arc traced by the particle is very small, and small arc length is nothing but it is a straight line. So here I can denote the length of the arc delta s as a straight line because it is very small. Small arc, what is it? It's a straight line. Is that clear? Fine. Now students, what I'm going to do is, I'm going to draw two vectors. Alright, vector AP and vector BQ. AP represents the velocity V1 of the particle at position A, and BQ represents the velocity V2 of the particle at position B. Is this clear? Two velocity vectors. Now, students, this is UCM. So we all know that the magnitude of the linear velocity of the particle is same. Magnitude is same, but direction is different. This cloud is very important. Is that clear to you? Fine. Now students, what I'm going to do is, I'm going to draw another vector BS, and this vector BS is equal to AP as well as parallel to AP. Is that clear to you? Fine. Now I'm going to draw one more vector, and this vector is your SQ. Alright, you see there. I'm drawing one more vector SQ. Is there any question till now? No. Fine. So what I'm going to do is, I'm going to carry this forward and let us move on with the construction. Now students, if you see over here, alright, we can apply triangle law of vector addition. Where we can apply triangle law of vector addition? See there, BSQ. There I can apply triangle law of vector addition. You have three vectors, BS vector, SQ vector and BQ vector. So BS plus SQ will be nothing but your BQ. So BS vector plus SQ vector will give you your BQ vector. I am using triangle law of vector addition. Is that clear? Now, what is SQ? Yes, SQ is nothing but BQ vector minus BS vector. So then I can write SQ is, now hold on, BS vector is equal and parallel to AP vector, yes or no? So instead of BS, I can write AP. So then I will get SQ is equal to BQ minus AP. Is that clear to you? Fine. Now next step, SQ is equal to, SQ vector is equal to, now see there. What is BQ vector? BQ vector is V2, velocity V2. And what is AP? AP is your velocity V1. So BQ vector is nothing but your V2, and AP vector is nothing but your V1. So SQ will become V2 vector minus V1 vector. Now students, we all know what is V2 vector minus V1 vector. It is a change in velocity, which is delta V. So SQ represents the change in velocity vector, delta V vector. This is clear to you. So here I'm going to stop because this is what is there in your construction. It is very simple. Okay. So I'm just going to disappear. I'll appear and we'll go on to the proof. Okay. Take care.
Okay.